In this module, we are going to be discussing regression models from an exploratory data analysis perspective. We'll begin with a quick overview of the previous session. We are going to talk about what is regression. We'll discuss the different types of regression models and how to choose these regression models. And we'll discuss some of the underlying assumptions of these models. So to give a quick recap of the previous session, we discussed a little bit about hypothesis testing, basically the main idea behind hypothesis testing when we were looking at the various choice of statistical tests available to us. So continuing in this journey, regression is also one of the tests that we can use. We discussed in the previous session how we can convert our research question into testable hypothesis, how we generate or decide upon the key metric or the statistic which is equivalent to that unknown population parameter that we are trying to estimate. How we convert our research question into a testable hypothesis. We looked at different examples, such as examples in which we are trying to compare two groups, or we are trying to compare our sample to some known specified value. We discussed hypotheses that look at association. And then we classified these hypotheses into four major types. So the first type is, does your sample come from a population having a specific value when you're comparing your sample to a specific mean or proportion value, the mean and the proportion being the statistic of interest. And then in the second type of hypothesis, we compare two groups. With respect to the mean and the proportion. In the third, you have multiple group comparisons where you convert your hypothesis into a multiple group comparison of means or proportions. And then we had the fourth, more generic type of hypothesis, which looks at, which is formulated in such a way so as to explore the relationship between our exposure or independent variables and the association with the outcome or dependent variable of interest. And that is where we use methods such as regression. So what is regression? Now, regression is crucial in biomedical research for understanding the relationship between your independent and dependent variables. It can be used to predict your outcomes or response or dependent variables. It is used to identify the risk factors or treatment effects of importance. It aids in uncovering patterns in complex biological systems where your traditional statistical tests like t-tests and ANOVA are based on a small number of variables. Regressions allow you to explore more complex patterns by incorporating multiple variables and their relationship with the outcome or multiple outcomes. So it allows you to study complex relationships too. So simply speaking, regression is a functional relationship that determines what you would expect the value of your dependent variable or some function of the dependent variable to be given that you have observed values of your independent variable. So you collect data on your independent variables, you have that data and you collect data on your dependent variable, and then you see that given these certain values of your independent variable, what would you expect the value of your outcome variable to be? And that expected value is a measure of predicting the outcome. So this functional form F which can take different forms, the simplest being the straight line equation form, and then there are different mathematical formulations. So the F here is a mathematical form, but it is an approximation of what is happening in the real world. We cannot always exactly model what is happening in the real world, but these functional or mathematical forms help you achieve a close approximation of reality. And that is what a regression model is. It is an approximation of what is happening in the real world. There are different types of regression models. You may have heard about some of these. You have the simple linear regression or multiple linear regression model. You have polynomial, you have ridge regressions, which are all linear regression in some way. And then you have non-linear. Logistic regression is a very commonly used model. And then you have hierarchical regression. So these are some, there are many others in the basket of regression models that are available to statisticians, but these are some of the very common ones. Now, when we say the functional form F, there are, as I said, there are different ways you can represent this functional form. On the left, you have the very simple functional form, which is y is equal to a plus bx. The a and b. So this is a straight line equation used to approximate the reality. The reality meaning the relationship between your independent variable in the x-axis and your dependent variable in the y-axis. This is a very trivial example, trivial equation, but a and b are parameters of your regression equation. Generally, regression equation, the parameters which are unknown, and these are the ones that have to be estimated from the data, although they have a mathematical form, they are generally also having some kind of a real world interpretation. So, for example, if this approximation of reality using this mathematical linear equation says that the expected value of body weight given a specific value of height is 80 plus 2 into height. So here the interpretation of the coefficient A and B in the real world, A, which is mathematically speaking the intercept, which means that it is the value of y when x is 0. That means if height is 0, y is equal to A, or in this case, weight is equal to 80. Now, in the real world, this interpretation is that the overall expected value of weight is 80 kilograms in your sample. The B parameter also has a real world interpretation, meaning that for every 1 unit increase in height, let's say the height is measured in feet. So every 2 feet increase in height, you would expect a 2 kilogram increase in body weight. So not only is this a mathematical equation, but the parameters of this equation can be used to interpret the real world parameters such as the rate of change and proportions, the rate of change in proportions, and so on and so forth. A percentage change with respect to a reference value. The equation that you see on the left-hand side of your screen is the well-known logistic regression equation, where you have the independent variable x, and the dependent variable takes binary values 0 or 1. And here we do not model the 0 or 1 itself, because we are not interested in predicting, you know, we are more interested in knowing the probability that a particular participant will have a value of 1. So here in logistic regression, we have binaries like success and failure, cured, not cured, having a disease, not having a disease, and such kind of binaries. We are more interested in the probability of the success, given that you have observed certain values of your independent variables. Why this is called a linear, non-linear model is because the parameters they become linear only when you apply a transformation. So that functional form f here is the logit function, the functional form that we saw in a previous slide. Here is the logit function, and hence it is not linear in the parameters. The parameters are some functional form. So that's how you come at you have the linear and non-linear regression models. In a previous session, we have looked at how there are certain criteria, and we are going to talk about them. So your outcome variable distribution may be highly skewed, but you can apply transformation and then use linear models, or you also have a choice to use non-linear models in the original data. We looked at an example where the relationship, the scatter plot is one of the very first techniques where you try to understand whether you would use a linear or a nonlinear relationship, or you can use a linear relationship, but you will need to transform certain variables. So this was an example where the original raw values of the data were showing in the scatter plot a curvilinear relationship, but you transform by transforming the independent variable and replotting the scatter plot, we found that there was a linear relationship, and so we could apply a linear mathematical formulation, and hence a linear regression by transforming the independent variable. Now, here also the parameters are estimated, but they may not have exactly the same interpretation. So whenever we are linearizing a non-linear scatter plot and we transform it using a functional formulation, we have discussed this in the previous session, we have to interpret the parameters accordingly. So in this case, we are not looking at a 1 unit increase in x corresponding to b units increase in y, but the interpretation now is more in terms of a percentage increase in the outcome for a certain percentage increase in the independent variable, because we have log transformed the independent variable. So the relationship is still now linear. The model is still linear, but we call it a linear log model. So how do we choose from the various regression models that are available to us? There are several criteria, and one of the primary criteria to start looking at a choice of regression models is first is research design. And in research design, for example, if you have a study in which you have say 100 individuals, and for each individual the outcome variable has been measured only once. So you have, let's say, a hypertension study where you are measuring blood pressure, and you are measuring it only once. The choice of regression models um, will be slightly different from vis-a-vis a research design where you are looking at repeated measurements. So for each individuals, let's say you have three time points of measurements in a study where you are looking at, let's say, pregnancy weight gain across trimesters. You have weight of each participant measured at first, second, and third trimesters. So there are repeated measurements, and there will be a certain degree of correlation between these measurements, which are your outcome weight. In the first design, we generally use regression techniques that will assume that the participants' measurements or the outcome variables are the values that we observed are independent of each other. In the second case, there is a correlation between the outcome values for each participant within each participants. And then there is a third kind of a data structure or research design leading to a hierarchical data structure. An example of which is having multiple schools or multiple primary health centers, and from each health center or school, you sample a different number of students or patients, and then you observe the outcome in these participants either at one time point or it could also be at multiple time points. And that is, you end up with a hierarchical structure where the outcome is affected by the intercorrelations and the variability of participants within each schools, and also between schools you have a variability. We will only give an overview of these. We are not going to go into the details of regression models over here. It is beyond the scope of this presentation. But for this kind of, the third kind of research design structure, we use the multi-level or hierarchical regression models, which are which could be linear or which could be non-linear in nature. Then the second criteria that we look at is the level of measurement of the outcome, whether our outcome is continuous. And within continuous also, we look at whether it is skewed, whether it is not skewed. Then categorical outcomes, whether it is binary, only two category outcomes, like we discussed, success, failure, cured, not cured. And disease, not disease, or there are multiple categories like low, medium, high. So, and then the variability in your outcome, which obviously is the spread, or which can which you gives you an idea also of the skewness, is also a determining factor in how you first think about choosing the possible regression models. So for continuous variables, we have already looked at it in the previous session. One of the very good ways to start off with is to draw, is to plot matrix scatter plots. These will give you an idea of how individual independent variables are related in terms of the pattern that they follow with respect to the dependent variable. They will give you an idea about the correlatedness. They also give you an idea about the correlation between the independent variables, which is very, very important when we are doing procedures like the linear or multiple linear regressions. So if you have very many independent variables that are correlated with each other, you are left with a phenomenon called multicollinearity. So there are many variables that could have the same explaining power, and you might end up with kind of a situation where you are overfitting your model. So this is a very simple diagram that kind of can give you a pathway when you start thinking about regression, starting with your outcome data. So this is more related to the 2 points, which is level of measurement and the variability and outcome. So when you start thinking about the choice of regression models that are available to you, so this flow diagram can help you arriving at um, uh, at a starting regression model. And then, of course, it is a very iterative procedure. It is not like a one-go procedure. Often researchers think that, you have this list of independent variables, you have your dependent variables, just fit one regression model. Your outcome variable is continuous. So, hey, let's just go for linear regression, and you fit a regression model, and that's it. So, but regression is a very iterative procedure, and we have seen glimpses of this in previous sessions where we talked about outlier diagnostics, where we looked at metrics like Cook's distance and Mahalanobis distance to identify outliers and inliers. So those are also part of your regression process. So as you can see, depending on the type of data, if you are dealing with numerical count data, then you have regressions like Poisson regression. So when we say count data, it could mean the number of T cells as an outcome variable that you're looking at. And we know that, things like viral load, T cells, these are all count data, and they have a lot of variability. So even in count data, you could be looking at count data that is very low variability, in which case you would use something like a Poisson regression model, or you could be having count data that could have a lot of variability, like T cells and viral load counts. And in that case, you would use something like a negative binomial. There was a study in which researchers were looking at, let's say, among people in the armed forces, their suicide attempts and their self-harm and ability to harm others. In such kind of stigmatized surveys, you will see that, the outcome variable, they may have a lot of zero value. So you have questions like, do you think about self-harm? And it would be, let's say, a 5-point scale as an outcome, and you start with zero, never think about self-harm, and rarely think about self-harm, sometimes, frequently, and so on. And that being your outcome, you can have these kind of outcomes tend to have a lot of zeros. So when you plot the histogram or the bar chart, you will see that there is a peak at the zero value. So in such kind of situations, you use something like zero inflated regression models, and the effect estimates will be like in the form of very well-known metrics like odds ratios, but they will not be your run-of-the-mill logistic regression models. So here, the outcome data, this flow chart helps you understand that given a certain count of outcome data, what could be your process flow for arriving at an appropriate regression model. So then what one of the key things that you need to decide when you are choosing regression models is variable selection strategies. And there are several techniques that are available, and no one technique is the holy grail. Each technique comes with its pros and cons. Uh, some domains tend to use or have a preference for certain kinds of techniques. So, in the context of exploratory data analysis, when you are beginning to explore your data from the perspective of what are the variables that you need to include in your model, the very first criteria is obviously what is your research framework? What are your independent variables that you have chosen? And you, when you did your research design, you would have a proper theoretical framework for choosing certain independent variables. So your first governing choice is obviously those independent variables. And then you have a basket of other choices. For example, you may begin by exploring the interrelations between the independent variables using a correlation heat map or a matrix plot. That would be your first step, where if variables are very highly correlated, there are certain alternatives available to you. You could either go for if your outcome variable is continuous, you could go for a partial least squares regression, because that is a very nice regression technique that kind of compensates for the correlation between independent variables. So it might be possible that your theoretical framework says that there are three variables that are highly correlated with each other, and all of them have to be in the model, despite the fact that statistically they might be demonstrating multicollinearity. And then you also might have a theoretical framework where all three of them are, need not be included. Any one of them is fine. So depending on what you have, you can choose an appropriate regression model. If multicollinearity is an issue, one of the things that you can consider is, dropping variables that are in order of priority. Keeping only the most important variable, or if all of the three variables are important to you, you could use a regression technique like a partial least squares regression. So as a very first strategy, you can explore correlations. Then you have processes like backward elimination, which is you start with putting all variables into your model, and then you have threshold values for your p-values. And based on those threshold values, if the variables are not significant, you start removing them from the model. And the thing with backward elimination is that if a variable is dropped, you do not have the liberty of including it back again into the model. Um, and then you have the forward selection, which is basically the reverse. You start with a null model, and then you keep adding variables one by one, and look at the p-values. If by adding an additional variable, the previous variable becomes non-significant, you drop it, exclude it from the model, and keep the new one, then start adding. So then the next one is stepwise selection, which is a combination of both backward elimination and forward selection. You may start it off with a backward elimination, and then in the next step, you do a forward selection, and so on and so forth. It's using these two, backward and forward elimination and selection, iteratively. And then you have all possible subset selection, which is very cumbersome if your number of variables becomes large. But it's a technique where you create all possible subsets of your independent variables and create different models, regression models out of these, and then you compare those models. So during your exploratory data analysis technique, these are something techniques that you can explore, and we'll start looking at them through examples. The first example is a hypertension risk study. So in this, the authors were trying to generate a hypertension risk score for middle-aged and older adults using regression models. A brief description is here on your screen. So the authors developed a hypertension prediction model for middle-aged and older adults using data from two community-based cohorts in the USA. The purpose of the study was to develop a simple prediction model or score with easy and routinely available variables. So basically, they were probably trying to say, if you have a certain hypertension score, what would be your risk category? Um, and you have certain independent variables, and your outcome variable is that risk score. The model was developed using 7,610 participants and 8 variables. So this is a list of your independent variables. You will see that some of them are continuous, some of them could be categorical. So there is no constraint on the level of measurement of the independent variables. You have smoking, family history of hypertension, whether diabetes or not, um, BMI, and lack of exercise. Now, candidate variables, that is the variables of interest, were selected based on scientific literature, which should always be, as I said, your first choice, a theoretical framework, some scientific basis, and the number of evidence. So in this, the authors applied the backward elimination variable selection technique to select variables for the final model with a conventional p-value threshold of 0.05. Now, the thing with these techniques is that you should always have a different threshold p-value for the selection and exclusion of variables than the p-value that you use for the overall, final model. So here, the authors used the convention threshold of 0.05. The study found that some important variables, theoretically important variables, did not contribute independently to the outcome following multivariate adjustment. Now, setting a higher threshold for the p-value and giving priority to clinical reasoning in selection variables. Now, what they are essentially, the critique is trying to say is that uh, putting a higher threshold, which means that instead of using 0.05, using something like 0.10, it by placing this higher threshold, you are able to at first include variables into your model, and then by looking at other metrics like goodness of fit and residual metrics, you can decide as an iterative procedure whether more stringent p-values are to be used. But as a first step, when you are doing exploratory data analysis for regression, the threshold p-value should be higher than your 0.50. And this is especially important, in the social sciences where, or in categorical outcomes, where you may not get very stringent associations. And so p-values of 0.05 may be a very, very stringent threshold to have. In this study, some important, clinically important variables were excluded, and a reanalysis showed that, if they had had a higher threshold, those variables could possibly be included in the model, and you could also have then had the effect estimates for those variables to create the hypertension score. In this second example, we look at there the researchers are trying to predict surgical site infections following a particular kind of surgery, laparoscopic bariatric surgery. So here they are trying to develop a prediction tool using a certain database. So regression for prediction. So in this, the authors developed a prediction model for SSI within 30 days of bariatric surgery. The objective was to construct a clinically useful prediction model. Clinically useful is important here, prediction model, to stratify individuals into different risk groups. An initial univariate screen was performed. So this is in the second example, they are doing first a univariate, which means essentially that, you take the independent variables one by one. So essentially you are using a forward selection procedure where you start with, a null model and you look at each of the independent variables separately. So variables that were checked further for clinical relevance with the outcome. Finally, a forward selection procedure with a P of less than 0.01. Now, this is even more stringent than 0.05 was applied among the selected variables in the univariate screen to build the prediction model. A total of 9 variables. So this is the list of variables that were used, and they were identified through forward selection procedures in the final model. Now, in the forward selection procedure, what you do, which is the reverse of the backward elimination, is you start with a null model and then you start introducing one variable, the clinically important variables one by one, and then you have a threshold of p values. If they are significant based on that threshold, you keep in the model, otherwise you drop. And here again, once you have dropped a variable, you cannot include that back into the model in the forward selection if you're using forward selection. And so in the final model, a p-value, that threshold of 0.05 in univariate screening and of 0.01 in forward selection. So it was more stringent. So that's why the critique says that this more stringent for the variable selection at the exploratory data analysis stage is a concern because it might eliminate some clinically important variables. Now, in the third example, which is of where the authors are looking at prediction models for the risk of new onset hypertension in ethnic Chinese in Taiwan. So again, some independent variables that might predict the risk of new onset of hypertension. In this study, the authors developed a new prediction model for hypertension risk in the Chinese population. A prospective cohort of 2,506 ethnic Chinese community individuals in Taiwan was used to develop the model. Two different models. So they have two different models. You have a clinical model and you have a biochemical model with 8 variables were developed. The variable for the model were selected using the stepwise selection method. Now, the stepwise selection method can have two approaches where you either start with the backward elimination approach or you can start with the forward selection. So in the backward elimination, you start with a full model, you start removing variables from the full model based on the cutoff threshold cutoff P, but you don't keep on eliminating. So there is a potential in stepwise selection to include a variable that has been dropped back into the analysis if it was clinically important and you would like to explore at different stages by including that particular variable, what would be the impact on your regression. So here they use that stepwise approach. But however, the critique for this study, and this is again a very important point, is that because you have different variable selection processes that are available to you, often researchers just mention the regression model that they have used, but they are not transparent about the way that the variable selection process happened, and because so many techniques are available, it is always a good practice to mention in your manuscript or in your report how did you arrive at the final selection list. It could be a very simple explanation saying that, all the independent variables were clinically, from the theoretical framework perspective, were important, and so we ended up using all of them. However, we did during an exploratory analysis do a backward elimination or a forward selection or a stepwise selection method also, just to see that in our data set, what is the significance level for these. So in the critique for this paper was in the element of transparency that they did not have when they did the variable selection. So method is mentioned, but how it was done is not mentioned. So now once you've done variable selection, um, and you've arrived at, let's say, a set of models, you could use multiple selections. So you use a backward elimination, and you also have a forward selection process. And let's say you also use stepwise, and then you are interested in knowing what would be a good regression model. So when we consider regression models, the very first thing that we would like a regression model to be is that it should be parsimonious or simple. Now, with the advent of big data, this term may sound obsolete, but in my biomedical research, in environmental research, this is still very, very important. Simplicity essentially means that you are trying to model a complex relationship with many, many variables, many of some of which you have measured and many of which you have not measured, and some of them may be immeasurable also. You are trying to incorporate them, uh, or you are trying to explain the phenomena, that is the relationship between your outcome variable and the independent variables that you have been able to measure using a very simplistic relationship. And sometimes a simple relationship may give you a fairly good explanation of what is happening in reality. So the very first thing that we need to take into account is a simple model is often a very good model, because the interpretability of simple models is also very good in the real world. So, for example, if you use a linear regression model, it is very intuitive. You can understand that the parameters represent the overall expected mean and the rate of change. If you are using a logistic regression model also, you know that we are looking at, let's say, the probability of change or the log odds of change. So parsimony or simplicity is a governing choice when you are looking at what would be a good regression model. Then the second criteria is a good model also minimizes the difference between what you observe and what you expect to see. So what you observe, you always observe your outcome variable also when you collect your data, and then you model it using a regression model. And what you model basically gives you what is your expected value of outcome variable or some function of the outcome variable given what you have observed. So if this difference, any model that kind of minimizes this difference or some function of this difference, it could be the squares of this. So this difference is called the residual. And in a previous session, we have looked at residuals and some functions of those residuals and how they are so important in identifying not only outliers but the choice of potential choice of regression model. So the residuals are used in what we call regression diagnostics. Again, important tools in the exploratory data analysis stage. So we have looked at these graphs before, where we looked at, the residuals contain information on whether the assumptions of the model that we are using are also kind of meeting. So for example, in linear regression, one of the key assumption is that the residuals should be normally distributed. Uh, And one way we already know from our previous session is that to see whether a particular variable is or values are normally distributed, we could either plot the histogram or the QQ plot. Once you have done a basic regression model, let's say a multiple linear regression or a linear regression model, you can look at the residuals, which is the difference between the observed value of y and the expected value of y. And this difference, when you plot the QQ plot, it should be following on the straight line. And that is when you know that, okay, your regression, the chosen multiple linear or linear regression model, or even the polynomial regression model, is a good model because the residual follow a normal, fairly normal distribution. Also, another very important graph is when for continuous outcomes is when you plot the residuals against the fitted value. Now, in this plot, this gives you an idea whether potentially there is a need to include polynomial terms. So, for example, height is to be included, as well as height square is also to be included, or let's say the temperature is to be included, as well as the temperature square also has to be included. This can give you this graph can give you an idea of that. And not only that, this graph can also give you an idea whether your particular model is overfitting or underfitting. So if you see the graph that is on the rightmost side of your screen, you have a central value of 0 on the y-axis, and then you have the negative scale and the positive scale on either side. So if you have a lot of residuals going above the 0 line, that would be an indication that, so if you look at the difference observed minus the expected, so positive residuals essentially mean that your observed value is higher, which means that your expected value is lower than the observed value, which means that your model is consistently giving you an expected value of the outcome which is lower than what you have actually observed, which is an example of underfitting. Similarly, if you have a lot of points going below 0, then that is an example of a regression model where it is constantly overfitting. So this particular graph at the explanatory data analysis stage, when you are looking at residual versus your predicted or fitted values from the model, can give you an idea about overfitting and underfitting. It can also give you an idea, let's say, if this graph is funnel shape, which this particular one is, gives you an idea of the violation of the assumption of another assumption of linear regression, which is for a given value of your independent variable, your outcome variable should be fairly normally distributed. So and your residuals should be normally distributed. That is a phenomena called heteroscedasticity. Again, we have discussed this in a previous session. So this particular diagnostic plot is very, very important to identify not only the assumptions of your regression model, but also the whether your model is kind of underfitting or overfitting or just right. So if you have these points scattered randomly about the line 0, then that means that the model is a good fit. So what determines your final choice? It is, as I said, the regression is a very iterative procedure, and it's not a one go technique that you decided, or that, okay, you have count data, you're going to use Poisson regression, you put all the variables in your model, and voila, you have your final regression model available. It is an iterative procedure. There are ways that you can compare models. We'll not go into the details, but there are some very well known. So for example, the metrics that are well known for linear regression are the R square, which is the coefficient of determination, which basically tells you the amount of variation in your outcome that is explained by that linear relationship that you have with independent variables. In the case of logistic regression, you have the pseudo R square. Uh, the R square is a measure of the goodness of it. So it tells you, you can express it in terms of percentages, and it tells you what percentage of your outcome variability is explained by your independent variable. However, the pseudo R square is more about model comparing. So let's say you have a logistic regression with 3 variables versus you added one extra variable, and then you calculate the pseudo R square for both, and then you test using a chi-square test, or which model is better, whether there is a significant difference between the two or not. And then you have other criteria like Akai's information and the Bayesian information criteria. The Bayesian is a little better than Akai because it provides a better balance between simplicity and the goodness of fit. And then you also have the likelihood ratio tests. Um, so uh, it's when we do regression from an exploratory data analysis perspective, uh, there are several things that we have to keep in mind. Obviously, simplicity and goodness of it is there, but we also have to first investigate, whether your estimates are being affected by the presence of outliers and inliers or not. And we have looked at these in previous sessions. You can refer to the slides in previous sessions where we looked at regression models where the effect estimates, that is the rate of change, be changed uh, a lot with the presence of even a single outlier. So those are iterative things that you have to go through. So you first start looking at multicollinearity, then you look at outliers, then you look at variable selection, and then you try to strike a balance between what is clinically important and what is statistically significant. And then you try to draw finally a balance between simplicity and the goodness of fit. So basically, this is an overview of regression analysis from the exploratory data analysis perspective. Obviously, each of these models are a master class, require a master class in themselves, where we can look at each model separately, and the particular metrics that are used for goodness of fit for each of the models. Here I've given you generic metrics. um, but the point to understand from an EDA perspective is that it is an iterative procedure.